Good afternoon. It's great to be back to again be talking about GSM. I want to take a somewhat wider focus this time, talk about related areas of GSM that since last year may have popped up as the new security features or suspected security features, and hopefully throughout the hour clear out all these suspicions that there may be security left in GSM. I'm delighted to be here with Sylvain Monod, programmer from Belgium and a mastermind when it comes to GSM protocols. Planning a couple of demos. Hopefully they'll work out, certainly well tested. So by the end of this, you will have seen a live GSM hack end-to-end, hopefully putting to rest the discussion over how secure these networks are and starting the discussion of how to secure them better. Taking a wider focus, as I was saying, on what makes these phones secure or what was supposed to make them more secure. However, we're not going to look at every single part of the GSM ecosystem. The research interest, fortunately, in GSM is increasing so fast that other people are looking at all the remaining parts of this ecosystem already. They're looking at the little computer phones we have now and how they're exploitable through malware. They're looking at the air interface, which is our primary focus of our research and of this talk. They're looking further into the networks, though, where the data that's being sent from the phone to the base station now propagates through an operator's network, perhaps through several operators' networks if your phone is roaming, and they're looking at data stored in backend systems. So all of this is a 20-year-old infrastructure. There's lots of private data and with little security. We'll be focusing on the one part of this security chain that's most exposed, the air interface, the data that's being exchanged between a phone and a base station. And hopefully get the idea across that on this air interface, much too little protection is provided for us to use it to transmit critical data. This is very much a follow-up to last year's talk and to last year's research, where the focus was much more narrow on cryptographic problems. And the GSMA, the umbrella organization of all the GSM providers in the world, rightfully remarked that looking at just cryptographic problems is not going to lead to a real hack of the system. No, it will never constitute an actual threat to call privacy. So they put towards us a challenge of please also identify your target and capture the data of your target before you apply your cryptographic insights of cracking keys and all that. So those missing pieces we want to deliver now to you, and a lot of this has already been released as open source software. The rest of it is some simple scripts that you as a researcher should be able to create yourselves, but that we won't release for their abuse potential, of course. What we want to demonstrate over the course of a couple of demos and the next hour is a scenario that works as follows. You become aware of somebody's phone number, just a phone number, nothing more, and you want to find where they are in the world, and you want to listen to all their calls and read all their text messages. And that's possible with cheap, very cheap, I should say, hardware and some open source software today. Let's get started. Three phases of the attack. First, find your target. Second, capture the data that target exchanges with the network. Finally, process that data to crack cryptographic keys and derive voice data from it again. Each of them will provide some theoretical background to make you appreciate the complexity, the number of steps needed to actually get this working, and then hopefully demonstrate each of them. So, locating a phone anywhere in the world. You'd think that's hard, but that actually, to some level of granularity, is the easiest part of this exercise. Due to the way GSM operators cooperate amongst each other. There's a global fabric, the SS7 network, that interconnects all the GSM providers that allow each other's users to roam in each other's network. So they need to be able to exchange information. As a side remark, all of this has been presented at this conference already a couple of years ago by Tobias Engel. So this is just a summary again, so you understand how all the different pieces are fitting together. So over this global network that the GSM operators use to coordinate, messages are exchanged such as, where's your subscriber currently? When I send Sylvain a text message, my operator will ask in Belgium where his phone is, and get as a response, he's currently in Germany, so send your text message to that location in Germany, it will then deliver to his phone. So it's a tracking service that's required for SMS delivery, at least how it was architected back in the day and still used in most networks. We can, of course, abuse this capability to track down people. Operators themselves can go much further than this so-called HLR query that's exposed on the internet, and even ask for what cell somebody is currently connected to. So while I'm getting the information that Sylvain's phone currently is in Berlin, but not in Hamburg, say, an actual GSM operator would get the information he is connected to the cell Alexanderplatz, Berlin, Germany right now. So much finer granularity. And any GSM operator can do this. We'll leave it at the LiDAR capability though, since that is exposed on the internet through providers that sell the service for marketing for pennies to the dollar. So the scenario goes as follows. You start off with somebody's phone number, you look it up through one of these HLR services. It tells you where to send your text message to if you want to reach that person, right? That gives you a city, or at least in rural areas, a rough location of that person. You want to increase that granularity by driving around that city and finding out which location area the person currently resides in. Location area is the next level down in granularity. Berlin will have a couple of location areas for each of the operators. So for each of the location areas, you start listening to traffic announcements in that location area, and you send text messages to the phone. You will either see text message being delivered as you send them or not. Gives you an indication of whether you are currently in the right location area or not. These text messages don't necessarily have to show on the target phone either. There's the nice function of silent text messages that do get delivered over the air interface, but never show on the phone. Where operators block silent text messages, you can send broken text messages. So text messages that the phone doesn't really understand. It's being delivered to the phone, and the phone will throw it away since it doesn't understand the type or anything about the text message. Right? Using this technique, you find where in a city somebody is. Last level of granularity, of course, is the cell itself. Driving around the dozen or so cells within a location area, again, using this SMS trick, you find what cell somebody is connected to. Right? And that's the first thing we want to demonstrate. Can we switch to the other projector, or to the other computer for projection, please?
Okay. So I'm targeting this phone. I know it's, well, here. So I know its location area just because here we only receive one, so there is just no question. I'm going to use one of these phones to listen to every mobile that gets paged So I'm just starting. Okay. Starting the phone. Okay. And then I have some Python script that basically sends SMS automatically, looks who gets paged, and try to correlate the various events on the network to find out where my target is. So here the two arguments are the phone number and the IMSI that I got from a HLR query. And these are some parameters that are transmitted and clear on the network. So I just grabbed them beforehand.
So basically, every phone is notified in the entire location area when a text message is about to be delivered to it. And then the phone is requested to announce that it's still there in the location area. And then the actual delivery will take place. We're only listening to the announcements ahead of time.
Okay, so but here it just collects some data to see who gets paged even when I don't send an SMS. Then I will send an SMS and try to correlate the various events. You just have to, it's all automatic from here, you just have to wait.
Mm-hmm. So we're solving an equation here with several unknowns. Not only do we not know where the phone is, which we're trying to find out, we also don't know the temporary identifier of this phone. The network will assign a new identifier to the phone every day or so. With this technique, we find both at the same time, though. By sending several text messages with a defined spacing, this pattern will show up as this identity receiving something from the network every 30 seconds, or whichever we set. And then we know, yes, it's here, and also what TIMSI, the temporary identifier it uses currently.
Yeah. So it sent the first SMS, and it got the delivery report from the network, so I know that the mobile was paged. And here you can see that there are two mobile that were paged that match my potential target, so I'm just waiting a little, and then I'll just do the same again, and hopefully there will be only one that was in both of them.
Mm-hmm. So the entropy of this, of course, diminishes as fewer phones are online on the cell. The more activity, the longer the search, since some other phone may show up as exactly receiving a paging in the spacing you set.
Okay, so it found a single match, and it says, okay, the TIMSI is 616B1A4C.
Let's verify that, yeah. So this phone has a nice monitoring mode where you can query it for all this data. 616B1, yeah.
A4C.
So now we know the phone is actually here, and we know it's TIMSI. So next steps. Can we switch back, please? Thank you. Now we want to grab data off the air interface that would allow us to crack the key, but then read that data given the key, right? Again, a little bit of background so you understand what's going on here. GSM phone calls use numerous different frequencies or channels to execute different phases of a call. Basically, a GSM call works as follows. The phone is listening to what's called the beacon channel, where all these announcements are happening, the pagings we just listened to. These were on the beacon channel. The base station, when say it wants to announce to the phone that it's being called and connect through the call, will ask the phone, "Are you still here? Please respond to this paging." And if the phone does respond, the base station will immediately say, "Okay, let's continue this discussion on a different channel to keep this beacon channel as free as possible." This could be a different time slot on the same frequency. This could be a different frequency. This could even be a set of frequencies among which the phone hops. The base station determines all of this, and it much depends on the operator configuration and their sense of noise resistance, mostly, what configuration they are choosing. So on this control channel, the phone is now typically asked to start encryption, with a key that's already negotiated between the base station and the phone. If no key is negotiated yet, it will happen now too on this control channel. So in any event, they switch on encryption, and only then the base station tells the phone what's going on, that it does receive a text message or that it does receive a phone call right now. Now, after basically sharing this information, the channel is changed again to also keep free this control channel that's used for different phones' control information. And now typically the base station will ask the phone to start hopping among various channels to increase the noise resistance, so that if on one channel there's a lot of noise, some data of the other channels still gets through to the phone. And this traffic on this set of channels is, of course, what we would want to intercept if, in fact, we wanted to listen to the phone call. So you appreciate that this is basically a multi-frequency problem with a moving, unpredictable target. Since the information where you would have to look already comes encrypted, right? These frequencies also are spread widely across the available GSM band. So they're not at all adjacent to each other and basically easy to sniff as a package. GSM 900, the T-Mobile and Vodafone allocated band in Germany, they use 35 megahertz of spectrum for each downlink and uplink, which is broken into packets for those two operators. And then each operator takes some subset of what they got allocated to a cell, typically spread across the spectrum for the set noise resistance. And then each phone call, again, gets a subset of the base station's allocation. And again, as widely spread as possible for noise resistance. So the signal processing or the signal capturing challenge is to capture diverse frequencies in two 35 megahertz chunks of spectrum. Right? And this channel has been solved a long time ago by intelligence and law enforcement suppliers. And starting on the right side of this slide, what they're using are custom, fairly expensive boards with big FPGAs and very fast AD converters. They can actually record and process an entire GSM band at once. Those devices come at 40,000, 50,000 euros, so they're certainly not a reachable research tool for us. However, the same idea has been shrunk to more affordable and more open hardware, programmable radios, USRP being one example. Those two use FPGAs and AD converters, both not quite as big as these commercial boards, to just suck down a configurable chunk of spectrum. With 4 of these USRP2s, you can again capture all of GSM 900. Right? We're talking something like 5,000 euros for those. The USRP1s are more limited in the amount of bandwidth they can transmit due to the USB interface. Some of you may already have them though, so they're certainly a useful GSM tool, and again, a little cheaper. I'm making a huge jump, again, in the limitation of frequency, but also in the price, come ordinary phones. Every phone should have the capability of recording GSM data, right? That's what they're built for. So taking a 10-euro phone, which is what these are, somebody should be able to reprogram it in such a way to act as a let's call it a debugging device for GSM, right? And that's what the Osmocom team, and among them Sylvain, did over the past year or so. And I'll let him explain all the loops he had to jump through to actually create a €10 GSM debugger?
Yeah. We started with those cheap phones, and at the start of last year, Harald and Dieter started writing open source baseband firmware for those phones, which implemented all the normal phone functions. So it could act as a real phone. Receiving raw GSM data is not part of a normal phone function. There is one main thing that gets in the way, and it's the DSP. Because basically, the GSM will transmit packets of information in bursts, and the first step of layer 1, things like encryption, forward error correction, and things like that, will be handled by the DSP itself, and then the DSP will give to the ARM core of the phone a reconstructed layer 2 packet. This is bad for us for sniffing, because we really want the raw burst output, because this is what Kraken wants, and so to debug we need this. So the first step was to patch the DSP. The DSP is ROM based, but you can patch some function in RAM, and that's what took most of the time, is to extract the raw burst data and basically disable all the higher level logic, forward error correction and things like that, and just get the DSP to give us exactly what it took from the air. It's not the raw IQ data, it's the demodulated bits. So we don't have to do the demodulation, and we enjoy the very good demodulation algorithm that TI wrote for their phones. So with this, we can capture one time slot of each GSM frame, because this is what a phone usually does. It only listens to its time slot. With a little more patching, you can actually get it to capture more than that. Currently up to 4, but you could go up to 6. There is 8 time slot in one frame, by the way. But the problem you encounter then is to get the data off the phone, because you only have the serial port, and you need to, with some special tricks and the non-standard baud rate, I'll skip the detail, but basically you need a faster USB cable to get all the data to the PC for processing. And when we've done this, we can get much more data. And one nice thing about the phone is that it can switch frequency very fast, because it needs that to follow. It's a normal phone function to follow hopping, which means we can even retune between the uplink and the downlink, so we can, with a single phone, capture both what the BTS sends to the phone and what the phone sends to the BTS, because they're slightly shifted in time, so we can retune between both. To do that, however, there is one additional step. If you're not very close to your target, like 20 meters or so, the phone has a filter that will try to reduce noise and only sends the good frequency to the radio in the phone. If you want to capture uplink, which is in a different frequency band, you need to remove that filter. And with this, you'll get like 100, 200 meters or so uplink listening range. So this is what I'm going to demonstrate now.
Exactly. Can we switch over to the other computer once again?
Okay.
Thank you.
Okay. So here I'm using 4 of these phones connected to 4 serial ports on my PC. I just need to start everything. And okay, so I started all the phones. Okay, the phones are started. And here I have another application where I tell him to listen to ARFkin 671. This is the cell, the only cell you get here for this provider. Okay, 4 phones, and here I introduce the TIMZ of my target. So I tell him, as soon as you see a conversation, some messages that are not for my target phone, you just drop them. I don't need them. I only want my target.
Mm-hmm. To emphasize this for any law enforcement or lawyer in the room. So we are sniffing on a live network, one of the commercial operators in Germany, but we're only sniffing data that's specifically sent to this very phone, since we found out its identity before. We wouldn't need to apply this filter, but to stay on the right side of the law. kind of wanted to.
Okay, so now the phone is just looking at every channel that's being assigned, and if it's not for my phone, it just drops the data. Now I'm just going to send a new text message to this phone. If I find this phone number. Okay. So here at some point I should see a text message. Okay, so this was it. Okay. I'm going to stop the capture now and try to show it. If I can find it back. Okay, here. I recognize it because I see the ciphering mode command, which is the order from the network to switch to ciphered mode. If it was not my SMS, I would have dropped the conversation before I even get to there. And here I see the paging. Okay, the resolution sucks. And yeah, this paging response is for my Team Zero. So this was the SMS. Okay, if I look here, these are all the conversations that have been recorded. As you can see, most of them are very, very small because there is only one packet, the packet that says if it was for this phone or not, except this one, which is bigger because it basically recorded the entire SMS. And that's it for now, I think.
Mm-hmm.
Yeah.
Back once again, please. Can we switch the display again? Thank you. So this is how we recorded data and displayed the data up until the point where it says, now please start encryption. So the logical next step is to crack that encryption, right? Again, tiny bit of background. The phone SIM card and the home operator share a secret key. That key is used for billing purposes and all of this, so it's really well protected since it protects the monetary streams of the operators. If you know that key, you basically make calls on somebody else's account. There's another key that's much less well protected since it only protects your private data. That's the That's the session key. And the session key is derived from this master key in the SIM card and shared with the phone, and it's derived in the backend system and shared with the base station. So now the phone and the base station have a secret key, a session key, that they can use to encrypt text messages, phone calls, and what have you. The name session key should suggest that this key is only used once for one session, but in fact it's recycled a couple of times, and then a new key is generated. We'll use this property in the next demo because we'll crack a key now, show each step, do the slow way, and use that key to crack the next data. I'm just going to go over this very briefly, since basically we discussed this a year ago here. The fact that the A51 keys are vulnerable to pre-computation attacks. We did release a set of rainbow tables a year ago that would allow a computer with this set of 2 terabytes in tables to crack keys in a couple of seconds. We have since improved the approach a little bit, well, actually significant, but with small steps, and computed a second rainbow table set. It's again 2 terabytes in size, but it's much lighter on the computational load. So a normal computer with just a CPU and maybe 4 or 5 hard disks can now crack keys. And how fast is yours? 20 seconds, roughly?
Yeah. Well,
yeah. So yet another component of the debugging tool set. For details, refer to last year's talk. The second table set has been put on BitTorrent, again, the faster one. But back to the data we just captured. What part of the data are we going to look at now? Well, certainly we're not going to look at the encrypted part, which, or the non-encrypted part, which we already displayed. The next packets, though, that weren't displayed in Wireshark since they couldn't be processed, were still recorded onto the hard disk in the encrypted version. And what's being encrypted in GSM is not the packet itself, but rather a transposition of that packet onto a larger number of bits for error resistance that chopped down in 4 bursts. So the quantity of data we work with when cracking keys is a burst. For all practical purposes, it doesn't really matter what we work with, since we're only interested in the encryption part of this message. In fact, what we need to do is predict what one of these bursts would be, right? And then see what's being transmitted over the air and derive from those two, the one guess and the one observation, what the encryption did. The encryption is simply an XOR of a key stream. So given 2 parts of an XOR, you can easily derive the third. And that's what we do. So for each burst we see on the air where we know the data that is encrypted, we can derive key stream. Now this seems very counterintuitive. Why would you encrypt something where a person who doesn't know the encryption key already knows what's inside, right? Seems waste of resources, in fact radio resources too. If we know what we should have received over the air, why send it in the first place, right? However, GSM has a lot of packets that consist of completely known data, especially in the call setup. Let me jump ahead a little bit here. We'll come back to the slide later. But just to show you the data as it's being transmitted over the air. This is the encrypted part of a call setup. It basically says encryption enabled, something like that. This encodes the number that's calling. This says, hey, I'm Vodafone in Germany. This says, here's a control channel, but I've nothing to tell you, so I'm sending you an empty message. And yet another empty message on this control channel. I'm Vodafone in Germany. And please jump to another channel so we can do the call. But before you do that, let me tell you that I've absolutely nothing to tell you on our control channel. Every call setup on this cell looks exactly like this, with the variation of the number that's calling. So that's the only variable in this entire exchange. And there's more messages like those that weren't shown on that slide that are as guessable. So, and exactly that's the second ability or capability we need to crack keys. First, we need a cracker that is fed with key stream, but also we need a guess as to what the message was so we can extract the key stream. And I'm assuming you already did that?
Yeah, sure.
Yeah. So basically this part we have already seen, how the phone is now tuned to the cell, but also filters for the specific TIMSI. It recorded a message as it was transmitted unencrypted. This is the message, hey, I'm Vodafone in Germany. And it then captures the same message encrypted. It's sent at very, very defined time slots. So you just XOR the two and you get the key stream, which is fed to this tool Kraken by Frank Stevenson. He's Norwegian, and I'm being told Kraken is like a big octopus. So this octopus eats A51 key streams. And let's try whether it's working. So can we switch back one last time, please?
Okay, so basically I just input to the, okay, guessing the burst is just annoying, so we have a software that does that. You just give it the file to the record burst, and it will try to analyze the network and try to guess the clear text traffic and output you exactly what you must input to crack in. So if I just run it, okay, it gave me some, each time it's like the layer 3 message that was guessed, and then the burst corresponding and what I must feed to Kraken. So I just, okay, I'm just gonna, okay, it is actually for an old version of Kraken that only did 1 burst at a time. The newer version actually can do 8, so I'm just gonna input all of them at once.
Yeah, this is a non-yet released version. Thanks to Sascha Chrysler for hacking this in the last couple of days. It will be released soon. You need 1 space there, yeah.
Oh, I screwed up. I didn't put this space.
No, I think it's good. So these are all the bursts. A combination of a guess, what data should have sent, XORed with data we actually saw on the wire, on the air wire, I guess. Yeah, and it's cracking, what, 8 bursts at once now.
Yeah.
And due to the load balancing, they'll all kind of finish around the same time. Should take a minute or so.
Oh, I'm sure it works. I've done it already.
What's that?
I'm sure it works. I've done it already. Okay.
So now we found what could be the correct secret state that was in the A51 encryption function when this data was generated. That doesn't exactly correspond with the KC, the session key yet. It may be a false positive. So there's one last step where we have to try basically using this key to generate another part of the conversation we observed. And in fact, it did find the KC. So this is an A51 session key for the entire call. Oh, let's continue this demonstration in so far as recording an actual call.
So I'm just checking that the key is correct, and so now I have, yeah, I've deciphered the SMS delivery, and you can see here, SMS deliver and where I send it from and everything. So this is the correct key for this. So now basically I'm just restarting the sniffer, but I'm giving it the current session key so that it can follow the phone wherever it goes, on what channel, and record the voice data as well. So the phones are still started? No, okay. Okay. So I'm just going to call that phone now.
Mm-hmm.
If I have network, yeah, okay.
So it is ringing. Hello, hello.
Hey, hi, Carsten. How are you doing?
Doing well, thank you. So I'm now providing data for the uplink, and you are?
I'm providing data for the downlink, since I'm listening to that phone. And so if I look at the data that has been recorded now, okay, it's actually this console. Okay, you can see that now there is one data file that is like much larger than the other ones, and all that's needed is to basically extract the raw GSM frames. We just need to convert that a little to get actual audio, and of course we have a tool for that. Okay, I'm just gonna need the.
That has been released already, right?
No, but this will be. It's just the code isn't clean enough yet for me to publish it. And since the bursts are still ciphered in this file, I need to provide the key that I used as well. Okay, it's processing. And it created two files, one for downlink and one for uplink, if I play them. Hopefully, we'll get audio. Oh, is the audio from my laptop patched in somewhere?
Hi, Carlton. How are you doing?
That's half of the conversation, of course, in the downlink. Yeah.
I'm providing this for the downlink, since I'm listening to that phone.
Let's do that too.
Providing data for the uplink, and you are...
Yeah.
So that, yeah, there you have it, a full uplink, downlink GSM sniffer with 4 €10 phones. All right, so we saw this data already and how ridiculous predictable it is. Fortunately, well, at least when looking forward and looking at things that GSM could cheaply do to improve, this data would not need to be predictable. Look at this last message, for instance. It only consists of 3 bytes.
Yes.
Oh, we need to switch back, please. One last time, sorry. This last message. It's 3 bytes, since saying that you have nothing to say is kind of a short message. The rest of this message, and every GSM message is 23 bytes long, has to be filled with padding. Right? This padding was standardized as the byte 2B for some reason back in the day when they didn't much think about security yet. There's no reason, though, that this has to be 2B. The phone is not processing anything after the first 3 bytes anyway. Everything is encrypted, though. So even that data that the phone discards before even looking at it is encrypted. This leads to the situation where we can easily guess these messages, of course, even though they carry so little entropy where this wouldn't be needed. Now, the GSM operators themselves, I think, based on the initiative by Vodafone, did standardize that, please, every 2B should be replaced with a random number. Very easy idea. You can think of the amount of changes in the code that's needed to replace 2B with a random number. So 1 line of code. Right? This has been standardized, though, over 2 years ago, and I've not seen it in the wild yet. So just 1 line of code seems to hang somewhere in the quality assurance of Ericsson, Nokia, Siemens, or whichever base station is used in your country. This needs to be rolled out quickly, though, since this really makes it much, much too easy. Now, randomizing everything with a 2B in it is an effective tool, even when there's only a short series of 2Bs kind of added in the end, when the message is almost 23 bytes long. Due to the error correction codes, these 3 bytes trickle down into every burst and basically spoil every single burst. So the error correction amplifies the effect of this measure. So even in messages that are, say, 22 bytes long with just 1 byte of padding, this would have a huge effect on cracking time. The only attack vector left then are messages that are completely full to begin with, where there is no padding. And that, from our observations in call setups, are only system information messages. Basically, the messages that encode, hey, I'm Vodafone in Germany, they also encode, and all my cells in this area are this. So there's long lists of cell IDs being sent. There's no standard yet for randomizing these, but of course there's a lot of enough entropy in these messages, so you should be able to play with these. And that's, from our perspective, currently the hottest research when somebody really wants to improve GSM, finding a way of randomizing system information messages. However, without going that far of kind of starting new research as an operator of how you can protect your customers better, there's already a list of things operators should be doing and haven't for years not. Starting, at least, so our perception, the highest priority should be, it's called SMS home routing. It takes away the attack vector where somebody locates you anywhere in the world. This attack is just too easy. One HTTP request and you get somebody's location in the world. That's unnecessary and can be patched away with this technique, home routing, where all the text messages are sent to the home country first and then delivered from there. So his operator from Belgium would always tell me, send it to Belgium, we'll take care of the rest. Right? In the same step, the IMSIs should be cut from the HLR queries, which again, some operators do, some others don't. But it's high on the wish list. Second, clearly is the randomized padding that we saw on the slide before, both for control messages, but also some form of randomization for the system information messages that's yet to be defined. Clearly, as high on the wish list also is do not recycle secret keys. Cryptographic keys, especially when they're called session keys, should be limited to one session. Some operators do this. One in Germany, for instance, uses a new cryptographic key for every text message you receive, but will use the one from the last text message for your call, and for the next call, and for the next call, and for the next call. So almost there, but not quite. Should be a small configuration patch, one hopes. Changing the TIMSI more often would make it harder to track people down and keep following them. It's meant as a privacy feature, and back in the day people thought changing it once a day would be sufficient. Now, given the exponentially growing attack capabilities in the community, maybe once a day is not enough anymore. Right? If you want to hide behind Tor, you don't want to have static routes for days and months and years. You want to keep saying a moving target. The technical basis there, again, configuration change, all that's needed. And then lastly, something that the operators tell us all the time, that's our base security. That's why you need a 50,000 euro FPGA board to follow our calls, frequency hopping. Now, we don't need a 50,000 euro FPGA board anymore, but it still is a security feature that makes it harder for calls to be cracked. Some operators, including commercial operators in Germany, even on cells that do have several frequencies, do not use frequency hopping yet. It's ridiculous. Nobody understands how you could possibly leave this out. So this too needs to change. And this is our wish list for next year's Christmas. We'll keep chasing the operators. Please do the same. Call them and tell them that that's what you want as a customer. So to sum up, GSM is insecure, and more so, the more that that is known about GSM. Pretty much like computers on the internet in the 90s, when they didn't yet understand what security was, they didn't yet understand how to deal with viruses. Pretty much in the same situation with GSM now. The research certainly isn't done. I meant it when I said we built a debugging tool. This is for you to use and for you to do to GSM phones what you did to the internet 10 years ago, and help phones to go through the same evolutionary steps that computers did go through in the past 10 years. So help us make this better and help yourself to be better protected with your private data. Thank you very much. Ja, bitte.
Now that everything is seriously broken, are there any questions?
Hello. I have a question for Sylvain. When you did the firmware upgrade for your phone, had you some trouble with the secure boot mechanism of the phone?
Oh yeah, there is none. There is no secure boot mechanism for this phone, so there is no problem.
How old is your phone?
2006, the Motorola C123 Ti Calypso. There is a secure variant, but this phone doesn't use it, and a lot.
Excuse me, which chipset, which processor?
Ti Calypso. It's
TI Calypso.
The osmocom.org
yeah.
website is going to answer all questions along those lines. It's a
but,
well-documented project.
But just by curiosity, for the phones available today commercially, there is always secure boot mechanisms implemented, or there are still some phones which can be patched.
These phones are still available.
Is still available.
And they're getting cheaper every month. Maybe not after this, but...
Hi, I'm working for a German telecom operator, not in the wireless division. My impression is that nobody puts any money into GSM anymore with more modern standards like UMTS or 3GPP, IMS. Do you think they are more secure than the GSM? ISIM, USIM?
A lot of structural flaws have gone away with 3G, but GSM hasn't gone away from our phones. Most 3G phones will regularly switch back to GSM for some calls, and the more iPhones suck up the 3G bandwidth for internet usage, the more phone calls will be pushed down to GSM again. So 3G certainly is no answer to GSM security problems as long as operators operate both in parallel.
Thank you.
Hello. It seems like upgrading the security of the system wouldn't be all that hard unless, of course, they had to upgrade the wiretapping capabilities as well. And so perhaps the holdup is that the security agencies can't figure out how to crack it if they add the randomness.
All the improvements we're asking the operators to put in place are on the air interface. Legal interception happens in a later stage of the network. So it's at a more central location. And that, we don't know how secure it is, but at least it's not accessible by everyone with a cheap phone.
Yeah, I was referring to the illegal interception.
True, yeah. Well, there certainly is an industry around GSM intercept, and these devices are being manufactured and sold. It's not by incidence that you can buy a 50,000 euro FPGA device that would suck down all of GSM. If there wasn't another machine that would then crack all the keys that you just intercepted. But it certainly isn't available to researchers.
Okay, some people from AC want to know where they can download the set of A51 rainbow tables.
What's the address? It's something like torrents. Let's see. That would be the address. Can you all read this? reflexter.com/E100 torrents HTML. That will give you torrent files, and it's widely spread on BitTorrent. Alternatively, If you're not sitting on a gigabit Ethernet connection to the internet, send us an email. We have been shipping them to random places in the world. So.
Okay, Wu-Tang asks if other phones are to be supported in the future.
Yeah, we just talked to Harald about the porting the Osmocom to another MediaTek, I think, chipset.
The MTK, yeah. However, porting Osmocom is not the only thing that you need to do to have a sniffer like we use here. You need to patch the DSP of the MTK as well. That means reverse engineering it, and so on and so on. So Osmocom acts as a real phone. Okay, if you want to turn it into a sniffer, you need some more work. But definitely, I'll look at it. That's all I can say for now. Yeah.
And it's all open source, and you're the community, so make it happen if you need it.
In the previous slide, you said that we're not able to crack data streams yet. So what are the main difficulties here?
Data, as in GPRS and Edge, is much less accessible. So basically, there's no sniffing hardware for it yet. That doesn't necessarily mean we can't build one, and I should add the yet to this statement. On top, though, GPRS uses another set of encryption ciphers. So it's not all that clear whether we can break them with the same methods. Before they're being published, nobody can really answer that yet. But let's say people are working on it, and perhaps next year at CCC.
Did you have to make any physical changes to the phones, and how involved were they, if so?
Yes, if you want to dump, I don't know where the person is. Okay, yeah. If you want to dump the uplink channels, there are hardware filters on the phone that you need to remove. If you don't remove them, this will work fine in a lab setup because you are so close to the phone that's listening that the signal is so strong that it just goes through the filters without problem. But for targets that are further away, the signal will be too much attenuated by the filter, and you need to remove it and replace it by some other component. It was posted on the mailing list, and there is a report on how to do it. As long as you can solder 0402 components, you're fine.
Yeah, right here.
Okay, another question from ISC. What German operator in Germany changes the encryption on every SMS?
We're not going to answer that. Find out yourself. It's get a USP Osmocom phone. Yeah, we're not going to put anybody down unnecessarily. Let's say all four have easy next steps they could take to become more secure. None of them have achieved the best practice level we've seen in other countries yet.
Okay,
Do you want to give the people on the other side a chance?
Okay.
Last year you mentioned that the GSMA was now recommending to use, I think, A5/3 for encryption. And you also mentioned that you weren't entirely sure that it was a good idea because you thought you saw some insecurities in there. Is there any progress on that front?
Well, I think the discussion basically fell asleep after people got the offers from Ericsson how expensive it would be to replace major parts of their network just to upgrade to a new encryption function. The attacks work the same way. They're just a couple of orders of magnitude more expensive. Balancing that with Moore's law means that upgrading to another 64-bit cipher, that in this case is a block cipher, not a stream cipher, will buy you a couple of years. And spending many millions for a couple of years more secured is probably not worth it, especially if there are other things you can already do today. There's one line of code, one call to Ericsson, please send us the new firmware, that probably has a similar effect, at least in improvement factor right now. Right? So probably no A53 anywhere anytime soon, unless somebody would build an entirely new GSM network where all components already know A53.
Okay, last question. Kato wants to know if the location does apply to UMTS2, the location with SMS.
Did you understand that?
No, I didn't understand the question.
Can you ask that again, please?
Does the location with SMS apply to UMTS2?
Oh, good question. Yeah, UMTS paging, I don't know how that works.
No, I don't know either how UMTS paging works, so I can't answer. Sorry.
But yeah, chances are it will have a similar mechanism. Yeah, we don't know yet though.
Okay, are there any more questions?
No more questions?
One?
Hi. So if UMTS is better than GSM in security, can I force my phone to not use GSM?
Depends on your phone. My phone, you can force it to not use UMTS, but not the way around. Yeah.
Yeah, same here.
We have there a question still left. Okay, last two questions.
So how did the operators respond to your research?
Not yet.
Oh, okay, good.
Have you done some reverse engineering on the GSM stacks of some phones?
The question is whether the project has done reverse engineering of GSM stacks on phones.
We replaced the entire stack on the phone, yeah.
Oh, okay. Yeah. Well, there used to be a full source code of a GSM stack on SourceForge for the same chipset but another phone. So people have been looking at that reference implementation and kind of getting ideas on how to create it as open source software. So it's some way of reverse engineering, only that they already gave you C code.
So in fact, each operator takes a reference design, a reference stack, and they use it in all phones.
We wouldn't know.
Okay. So
Okay, give these guys a round of applause.
Thanks a lot. Good questions.